Imagine a universe where time is not absolute, where gravity is a curvature in the fabric of space-time. This is Einstein's theory of relativity, a revolutionary idea that shattered our Newtonian understanding of the cosmos. A universe where light bends around stars, time slows near massive objects, and gravity is redefined. Einstein, with his wild hair, unveiled these secrets, changing our perception of reality. He once explained, "Put your hand on a hot stove for a minute, it seems like an hour. Sit with a pretty girl for an hour, it seems like a minute." That's relativity. This captures relativity. Time is relative to our frame of reference. The laws of physics are the same for all observers in uniform motion. Whether standing still or traveling at light speed, the fundamental laws remain constant. Our experience of time and space changes with our relative motion. Before Einstein, physicists viewed space and time as separate entities, a rigid framework against which the events of the universe unfolded. Time, according to Newton, ticked at a constant rate throughout the universe, unaffected by the motion of objects or the presence of gravity. Space, too, was considered absolute and unchanging, a vast, empty stage upon which the cosmic drama played out. Einstein proposed that space and time were not separate entities, but were inextricably linked, forming a unified fabric called space-time. Imagine space-time as a vast, flexible sheet. The presence of mass, like stars and planets, creates a curvature in this sheet, much like placing a bowling ball on a trampoline. This curvature is what we perceive as gravity. Objects, even light itself, traveling through this warped space-time, follow curved paths, drawn towards regions of greater curvature. Einstein's theory of relativity didn't invalidate Newton's laws of motion. Rather, it provided a more complete and accurate description of gravity, particularly in extreme environments where Newton's laws break down. Relativity revealed that gravity is not a force acting at a distance, but a manifestation of the geometry of space-time itself. Albert Einstein, the father of relativity, was not a child prodigy. He was a late talker, leading some to believe he was slow. Young Albert's mind was already grappling with profound questions about light and space. His father gifted him a compass, a pivotal moment in his life. The compass sparked a sense of wonder in young Einstein. He was captivated by the invisible force guiding the needle. This fascination with unseen forces drove his pursuit of understanding gravity. Einstein clashed with traditional teaching methods, preferring independent study. Despite setbacks, his passion for physics never wavered. After graduating, Einstein struggled to find a job in academia and accepted a position as a clerk in the Swiss Patent Office, where he published his groundbreaking papers on special relativity. Einstein's genius lay not only in his mathematical prowess, but also in his ability to conduct thought experiments, visualizing complex physical phenomena in his mind. One of his most famous thought experiments involved imagining himself chasing after a beam of light. He wondered if he could travel at the speed of light. What would he see? Classical physics suggested he would see a stationary wave of light, but Einstein realized this contradicted the laws of electromagnetism, which stated that light always travels at a constant speed. This realization led him to a profound conclusion. The speed of light is constant for all observers, regardless of their own motion. This led to the development of his theory of special relativity, which deals with the relationship between space and time for objects moving at constant speeds. Perhaps the most famous equation in all of science, E = mc2, is a direct consequence of Einstein's theory of special relativity. This deceptively simple equation, which states that energy, E, is equal to mass, m, multiplied by the speed of light, c squared, unveiled a profound truth about the universe. Mass and energy are interchangeable. This equation implies that even a tiny amount of mass can be converted into an enormous amount of energy, a concept that would later form the basis for nuclear energy. The immense power of the sun, for instance, is a result of nuclear fusion reactions in its core, where a small amount of mass is converted into a tremendous amount of energy, according to Einstein's equation. E = mc2 also has profound implications for our understanding of the early universe. It suggests that the universe, in its infancy, was an incredibly dense and hot soup of energy, where mass and energy were constantly interconverting. As the universe expanded and cooled, this energy condensed into particles, giving rise to the matter we see around us today. Einstein's theory of relativity, while elegant and profound, makes some bizarre predictions about the nature of space and time, predictions that seem counterintuitive to our everyday experience. One of the most startling predictions is time dilation, the idea that time can slow down or speed up depending on your relative motion and the gravitational field you're in. Imagine two identical clocks, one on Earth and one on a spaceship traveling at a significant fraction of the speed of light. According to relativity, time would pass slightly slower on the spaceship compared to Earth. This phenomenon, though seemingly strange, has been experimentally verified numerous times. Atomic clocks, incredibly precise timekeeping devices, flown on airplanes and rockets, have shown slight but measurable time differences compared to clocks on the ground, confirming Einstein's predictions. Another mind-bending prediction of relativity is the curvature of space-time in the presence of massive objects. This curvature, which we perceive as gravity, can bend the path of light, a phenomenon known as gravitational lensing. These predictions, though counterintuitive, have been confirmed through various experiments and observations, solidifying the theory's place in modern physics. Einstein's theory of relativity, once a revolutionary idea confined to theoretical physics, has become an indispensable tool for modern science, shaping our understanding of the cosmos. Astrophysicists, armed with Einstein's equations, can now probe the depths of space and time, unraveling the mysteries of black holes and the Big Bang. One compelling piece of evidence supporting general relativity came from the observation of starlight bending around the sun during a solar eclipse. This prediction was confirmed in 1919, when astronomers observed the apparent shift in star positions, providing the first experimental verification of Einstein's theory. This observation validated general relativity and ushered in a new era of astrophysics, where gravity was seen as a curvature in space-time. Einstein's equations of general relativity predicted the existence of gravitational waves, ripples in the fabric of space-time, produced by the acceleration of massive objects. These waves, traveling at the speed of light, carry information about the most violent events in the universe, such as the collision of black holes and the explosion of supernovae. Detecting these elusive waves, however, proved to be a daunting task, as they are incredibly weak and interact very weakly with matter. It wasn't until 2015, a century after Einstein first predicted their existence, that scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, made the groundbreaking announcement they had directly detected gravitational waves for the first time. The signal, a faint chirp lasting a fraction of a second, originated from the merger of two black holes billions of years ago, a testament to the power of Einstein's theory to predict phenomena that occurred in the distant past. This discovery opened up a new window into the universe, allowing us to study objects and events that are invisible to traditional telescopes, such as black holes and the moments after the Big Bang. Einstein's theory of relativity, once a realm of abstract thought experiments and complex equations, has had a profound impact on our everyday lives, shaping the technology we rely on and deepening our understanding of the universe we inhabit. From the GPS navigation system guiding our cars to the satellites beaming down television signals, relativity plays a crucial role in ensuring the accuracy and functionality of these technologies. The Global Positioning System, GPS, a network of satellites orbiting Earth, relies on incredibly precise timekeeping to determine our location. These satellites, however, are moving at high speeds and are subject to weaker gravity than objects on Earth's surface. According to Einstein's theory of relativity, these factors affect the flow of time, causing the clocks on GPS satellites to run slightly faster than clocks on Earth. To account for this time dilation effect, engineers have incorporated Einstein's equations into the GPS system. Without these relativistic corrections, the GPS system would be inaccurate, accumulating errors of several kilometers per day, rendering it useless for navigation. This is a testament to the practical applications of Einstein's seemingly abstract theories in our technologically advanced world. Albert Einstein, the iconic physicist who revolutionized our understanding of the universe, was not just a brilliant mind, but also a relentless seeker of truth, driven by an insatiable curiosity to unravel the mysteries of the cosmos. His journey, marked by both triumphs and setbacks, serves as an inspiration to aspiring scientists and curious minds alike, reminding us that the pursuit of knowledge is an ongoing process, fueled by passion, perseverance, and a willingness to challenge conventional wisdom. Einstein's legacy extends far beyond his scientific contributions. He was a passionate advocate for peace, social justice, and education, using his platform to speak out against war, discrimination, and the dangers of unchecked nationalism. His humanitarian efforts, often overshadowed by his scientific achievements, serve as a reminder that science is not merely about equations and theories, but also about using knowledge to create a more just and compassionate world. As we continue to explore the cosmos and unravel the secrets of the universe, Einstein's spirit of inquiry, his unwavering belief in the power of human reason, and his commitment to making the world a better place serve as guiding principles for us all.